Okay, so yesterday we started to do some to analyze stochastic differential equations in general. This is all, everything is familiar now to us, that we have to interpret this equation. And the two main interpretations are Ito and Stratonovich. And we saw these three properties, which are very important. So these three properties is also, they are as a guide to understand what is the which interpretation should we use if we have an equation like that, and which one which one we should use. So let me erase here. And in this table, I summarize the main properties of each one. This is what we have discussed. In the Ito interpretation, the noise and the process are independent, so the product is zero. The average of the product is zero. Whereas in the Stratonovich interpretation, this is hard to calculate. You have to use some theorem, and it's hard to calculate. On the other hand, in Ito, you have to use this Ito's calculus, or and Ito lemma, and in Stratonovich you can use standard calculus. So when we have this, well, it depends. Sometimes you don't really have a theory that in physics, for instance, it's not common to have a theory that gives you a stochastic differential equation like that. Usually you get equations using Boltzmann equations and things like that. You get equations for the probability density. And then from the probability density, you go to the stochastic differential equation. So in this case, there is no any problem. We will see this in a moment. If you have this equation, and if the noise comes from intrinsic continuous time, so this is the case in many physical situations in physics and chemistry, then you should use the Stratonovich, as we saw in this third property here. No, when we saw that if the noise is color noise, then you have to go to Stratonovich. And when do you find Ito? Also, we mentioned that in Ito you are always evaluating the process in the first point. So it's usually used when you have discrete time, like in the stock market, for instance. If you have a model for a stock market for the prices of stocks at each day, at the end of the day, for instance, then the price on tomorrow is the price today plus some noise. So this scheme is exactly this one, and then for systems with intrinsic discrete time, but of course the time is discrete, but you want to do some continuous limit, then usually Ito is the one that you find. But you have to be very careful in any case with the derivation of the. So usually you don't get this. You derive this from something. So in the derivation, usually you should derive as well what is the good interpretation. This is if you just find the equation. But sometimes the interpretation is also a kind of tool. For instance, if you have additive noise, as we have seen here, with additive noise, the two interpretations are equal. So you can use either one or the other. So it depends, depending on what are your purpose, you want to use one, or you will use one or the other. And for instance, since this property is very nice, we can use Ito. Let me do this in an example. Suppose you have, this is something that we are going to study in detail later on, but it's the velocity of a Brownian particle. So we have seen that the position of the Brownian particle is the Wiener process, but this is for an overdamped particle. We will see this in detail. But if you have a mass m, so you have a particle with a mass m, the correct equation for the velocity is Newton's equation. So mass times acceleration is equal to the force. And what is the force acting on a Brownian particle? So you have a friction. This is given by the Stokes function. This will be the equation. This V, sorry, is the same as this one. I use a different, but the velocity, this is just the equation that you have, the deterministic equation that you have for a particle in a fluid, where the friction is given by the Stokes formula. So it is proportional to the velocity. And this is the friction constant, which has to do with the shape, the size of the particle and the viscosity. What Langevin did, this is the Langevin equation, was to include a noise to this equation, and the noise is white. And this is the Langevin equation, which describes this is the Langevin equation, which describes the velocity of a Brownian particle in the underdamped. We will see later on that the overdamped is the one that gives the Wiener process, but this is for underdamped with so a particle with inertia. So you have a mass here. Okay, if the mass is very small or gamma is very big, then this V goes to the white noise, because essentially what happens is that if M is very small, what happens is that V is equal to the noise divided by gamma. We will see this later on. Okay, so this equation has no problem of interpretation because the noise is additive. So the two interpretations are equal. So we can use any of those. And this is actually why in many books of statistical physics, non-equilibrium statistical physics, you see this equation, and those books don't talk about any Ito, Stratonovich, and so on. I think now is a it's more correct to introduce the whole theory of stochastic differential equations. But in many books of statistical physics, you see the Langevin equation, and there is no any comment on Ito and Stratonovich interpretation. Why? Because it doesn't matter. Here it doesn't matter. So both interpretations coincide. This means that we can use both interpretations if we like. But if we use one, we have to be consistent. So if we use Ito, we have to use Ito calculus, and if we use the Stratonovich, we have to use the normal calculus. So let's try to find how the energy evolves. No, let's think that we want to see how the Brownian particle, how the energy evolves. Since this is a free, there is no any extra force, so the energy is just the kinetic energy. So the kinetic energy is 1/2 mvt squared. So now we want to have an equation, an evolution equation for the energy. And in principle, this is like a change of variables. So if we want to calculate how the energy changes in time, this is a change of variable. And now, yes, we need to adopt one or the other interpretation. So let's adopt Ito, for instance. So we know that in Ito, this will be the result in a standard calculus, not a chain rule. So the derivative of E is the derivative of this, which is 2 goes here, so it's mv times the derivative of b. This is the chain rule. But we know this is, if we interpret this as a Stratonovich, this will be okay. But we want to go for with the Ito interpretation, so we need the Ito term here. And the Ito term, sorry, this is for a Stratonovich. This is what it is. This is for a Stratonovich. Sorry, so if we use the standard calculus, this gives us a Stratonovich. So we have minus gamma v squared. You see that mv dot is, we replace here, so we have minus gamma v squared v. But we have to interpret this as a Stratonovich. So this is a Stratonovich. Let's try to do it with Ito now. So with Ito, we have to use Ito's lemma. So it's better to write everything. You remember that we always have x dot equal fx plus g noise. So it's better to write the equation like that. This will be our f. and this will be our G. G is 1 over m. So we can apply the Ito's lemma here, which is this term, the same term as the Stratonovich, plus the second order term. Remember how it was that? Sigma squared divided by 2, and then G squared, sorry, G squared, and this m comes from, well, comes from this one, from MB. And this is the Ito term. This is E dot. So now we replace B dot by the differential equation, and we get the same thing. Plus, we get the same thing as Stratonovich plus the Ito term. The nice thing here is that if we now average, we know that the average of this is 0. Whereas here, if we average, we don't know what is. Actually, by comparing this with this, you can infer what is the mean value of this. The mean value of this is precisely the Ito term, but here it's more clear. So if we average the time derivative, we get that. We multiply by m divided by m, so we get this term. This is a dissipation term. You see that the energy is going to 0 exponentially, but now we have the Ito term, which is a term that it is a power. It's actually, you see that what is the physics behind the Brownian particle? There is a dissipation, so the particle dissipates energy, and this is this term. But now there is a fluctuation, and the fluctuation, what the fluctuation does is to introduce energy into the system. So there is a constant. This is energy per unit of time. So this would be like a power. So you have a dissipation power, and here you have an input power, which is due to the thermal fluctuations. It's due to the noise. Well, and we were able to derive this equation because we have used Ito. So you see, even though I've said before that if in continuous time, the Stratonovich interpretation is more plausible to use, since here we don't have any need of interpret this equation, we just can go, we can choose the interpretation which is more convenient for the mathematical calculation. So there is nothing fundamental here. It's just mathematical. The two interpretations are mathematical tools, each one following different rules. Stratonovich follows the standard calculus, but this is non-zero when we average it, and for Ito we need the Ito term, but this is 0. So these are tools, mathematical tools. By the way, from this equation, you could say, why the energy, there is this dissipation, but there is an input energy. Why this input energy? Well, this energy is the energy that the thermal bath, the surrounding, is putting into the system, and it's actually due to the thermal fluctuations. And so the energy doesn't go to 0, and we know that. We know that in equilibrium, this is something that we studied when we studied the canonical ensemble. We know that the energy, because of the equipartition theorem, is 2 divided by kT. Sorry, it's kT divided by 2. No, this is the kinetic energy. So in equilibrium, this means equilibrium. In equilibrium, well, in equilibrium, the power is 0, so the input power cancels the output power, so the energy doesn't change. So this is 0. So sigma squared 2m, which is the input power, equals the dissipation power, which is 2 gamma m, and the value of the energy at equilibrium. But the value of energy at equilibrium is kT divided by 2. So if you take these two equations and then cancel 2m, so you see that sigma squared, the intensity of the thermal noise, is 2 gamma kT. This is an important result because it's a result that equals or it's a relation between the dissipation and this input power, which is due to fluctuation. So it is a relationship between fluctuations and dissipation, and this is called the fluctuation-disipation theorem. It's the simplest form of a fluctuation-dissipation, which was due to Einstein, and it's called fluctuation-dissipation FDR, fluctuation-dissipation theorem or fluctuation-dissipation relation. And this is one of the particular cases. There is a lot of this is a general result that fluctuations in any system and dissipation are related by the temperature, and this is a particular case, which it's interesting because this tells us now what is the correct Langevin equation for a particle. We now we know now what is the correct Langevin equation for a particle. And you see, we have derived this result very easily by using Ito's lemma and Ito calculus. And we will study the Langevin equation more in detail in the next sections. Okay, this is the FDR. So yeah, just a reminder that although I presented this table, this is just a question of convenience to use the Ito and Stratonovich. This is because the noise is additive in the Langevin equation. If it is not additive, then the derivation of the equation should tell you what is the interpretation to use. Okay, now let me introduce an important result, which is, okay, we have the two interpretations. We would like to have a kind of way of going from one to the other. So this is the next result, that if we have an equation interpreted as Ito, for instance, so like that, so you have this equation, which is Ito, and X is the solution. So we would like to know what is the equivalent Stratonovich in a Stratonovich interpretation. So the idea is to find the equation that XT obeys in the Stratonovich sense. And this turns out to be this one. This is it. So these two equations are equivalent. The first one interpreted as Ito and the second as Stratonovich, they are the same. The solution is the same and they are the same. So this is the way we can go from one to the other. You see, if G is constant, then G prime is 0, and so this term doesn't appear and the two are equivalent. So this generalizes our previous result that additive noise doesn't need an interpretation. So let me prove this because the proof is interesting. The idea is the following. The idea is to go from this equation. We start with this equation interpreted as Ito, and we go to we change variable in such a way that the equation for the new variable has an additive noise. So the appropriate change is this one. Of course, there must be some. It's the antiderivative of 1 over G. Of course, one needs to have like some properties for G and so on, but let's assume that G is not 0 or that 1 over G is integrable and so on. We will see later on what happens when G is 0. When G is 0, it's a bit strange that you see when G is 0, the noise suppose that G is 0 at x0. So at x0, there is no noise. So then the x dot at that point is either positive or negative, depending on the sign of f. So it's a region that once you cross it is a point when the zeros of G are points where once you cross them, you cannot go back. So this is also called a boundary. So, but anyway, we will assume that G is not 0, so we can make this change of variable. Okay, now let's calculate the derivatives because we are going to use Ito's lemma. So we need the first derivative, which is 1 over g, and the second derivative, which is g prime minus g prime over g squared. And now let's apply Ito's lemma to find what is the equation that y obeys. So we have y prime, and as always, we have we have the derivative dy over dx, no? So now we have x dot. But now we have the Ito term, which is sigma squared divided by 2. And remember, the Ito term is the second order in the Taylor expansion of dy. So it will be the second derivative of y, which is with respect to x, which is minus g prime g squared. And here, and that's it, no? No, and g squared, sorry, g squared. You remember that g squared appears because, well, this is the Ito lemma that we studied in detail. So we have this equation, and now g cancels with g here, which is the important thing. So we get an equation. This is, by the way, Ito's lemma. We get an equation with this deterministic part. No, this is well, g squared cancels with g squared here. So this is the deterministic part, and now we have the noise, and the noise is additive. So now with this change of variable, we have a new equation where the noise is additive. So if the noise is additive, there is no any interpretation. There is no need of interpretation. So this equation is equivalent for Ito and for Stratonovich. So now we can interpret this as a Stratonovich. So we interpret this as a Stratonovich, and we go back to x. So we and do the change of variable, but using, instead of Ito's lemma, we use a standard calculus. It's a smart, so now we get xy. We need the derivatives. So for a standard calculus, we only need the first derivative, and the first derivative using the implicit function derivative theorem is g. Okay, so now we can go and say x dot is the dx dy, so it's gx times x dot times y dot. No, this is a standard chain rule. And now we go here, we put what it is, the value of y, and then we get g fg minus sigma squared prime plus noise. Then this g cancels with this one, and we have this. And now this equation is interpreted as Stratonovich. This is very interesting. This is why I like this proof, because it is a very simple proof. It's just to take the idea is to take let's put numbers in these three equations. So this is the original equation 1, and this is 2, and this is 3. So we go from 1 to 2 using Ito's lemma, no? And now we are in 2. In 2, there is no any problem with interpretation. So this is like a neutral region. So we can go to 3. We have gone from 2 to 3 using a standard calculus. So this is the smart idea, that if we use Ito's lemma, we have in a region where when here, this is Ito's realm, Ito's zone, let's say, and here is a Stratonovich. And in the middle here, there is no, this is like a neutral zone, because there is the noise is additive. So we can go, 2 is equivalent to 1, and 2 is equivalent to 3. But 1 has to interpret in the Ito sense, and 3 has to be interpreted in the Stratonovich sense. And this tells us what is the relationship between the two. Okay. Any question? No. Okay. So let me erase and let's do an example, because it is also interesting to do an example. So we have the equation that we have used now, which is this one. Well, I put now the noise with plus instead of We have seen this example with alpha plus noise, but it doesn't matter. The noise, the sign of the noise, this doesn't matter. You see that always we have g squared, so the noise is of course symmetric and the change of sign, so you can replace plus by minus without, and the results are the same. So let's try to now let's interpret this as Ito, and now let's calculate the equivalent Stratonovich. And the equivalent Stratonovich, so we have just to go there and put the formula. So we have x dot equal minus alpha x. Now I have to add this term, which is sigma square divided by 2, and now g is x, so g prime is x plus the noise. We should have put here a small circle to indicate that this is a Stratonovich. And well, we can write it like that. So you see that the Stratonovich has like redefined the parameter alpha by this quantity and this one. Now we could average. If we average here, we get this is 0, and if we average here, this is not 0. And actually, you can see more or less that this should be equal to this to cancel the two terms. But okay, you can do a lot of things with this. So this is an example, and it's a useful tool to sometimes go from one to the other. Actually, we are going to use it now in a moment. Okay, so let's go to the next point, which is the last point of the theory of stochastic differential equations, which is the Fokker-Planck equation. The Fokker-Planck equation, so we have seen the stochastic differential equation in physics. We usually refer to the stochastic differential equations as Langevin equation, although Langevin equation is only for the Brownian particle, but for any stochastic differential equation, sometimes we use this. And the Fokker-Planck, the Langevin equation or the stochastic differential equation is an equation for X, for the stochastic process. So it tells us how the stochastic process evolves. The Fokker-Planck equation is an equation for the probability density. So it's an evolution equation for the probability to find the system in a state X or in position X at time t. This is a probability density. And this evolves with some equation, which is actually the one that usually we use more, because the stochastic differential equation, well, we can integrate, we have integrated some of the simplest ones, but it is not so easy to handle a stochastic differential equation. Whereas the Fokker-Planck equation will be much easier, okay? So let's do it. Let's do it for Ito. And you will see that the Ito interpretation is very useful for this derivation. So we start with an equation like that. We interpret it as Ito. And the idea to derive a rho is to look at how this equation induces evolution in any average. It's a kind of, it's a smart trick to do. So we consider a variable. Instead of X, we consider any variable. And we will try to find how the average of this variable evolves. So we have an arbitrary variable of X, and now we want to find an evolution equation for this variable. So we have the Ito's lemma. And then this is the derivative of A with respect to X times X dot. Okay, I will denote with prime the derivative with respect to X, and with dot the derivative with respect to t. So A prime is the derivative of A with respect to X times X dot plus the Ito term. And the Ito term, remember, is the second derivative times G squared. And that's it. This is the change of variable. Okay. Now we average. And this is, sorry, there is a There is, oh no, there is a, this looks like a bracket, but it's an angle, one of these. So we average. And now it's the nice property of the Ito interpretation. This is 0. So the noise disappears and everything we get A prime. I will shorten the notation, so I will use just A prime times F plus sigma square A second G square. So we have this this nice equation. Now remember what is what is an average? An average is just the integral over rho xt. You see, now it appears this. So we have this equation is true for any A. We have not specified A, so this is true for any A. So from this equation, we can get the information of rho xt. This is the idea. If we introduce this formula here, so now we write this equation in terms of rho, we get the following. The first term, well, this is, if we make the derivative with respect to time, no, this is the derivative with respect to time, we get partial rho with respect to t, and here we get rho fa sigma squared divided by. You see, this is a prime f, this is the mean value, so I change the order, fa prime times rho, and here g squared a second times rho is the average. So we have now an equation that it is for any A. So from that, we should get the information of how rho evolves. But you see that here is A prime, A second. The idea is to get this derivative with respect to X out of A, and then get an equation where everything is A times something. Okay, you will see in a moment. So the idea is to get these two terms and try to get rid of the derivative of A. We can do this by integration by parts. So let me do it with the first, and now I will use all the notation. So this is this term, rho f A prime. And remember that prime, it means derivative with respect to X. So now we can make a integration by parts using this as one of the factors and rho f another factor. So we have the derivative. We have first the rho f a in the evaluated in the limits of integration. Let's put two limits of integration now, although I didn't specify it. It could be minus infinity plus infinity, minus the derivative of the first factor. So the derivative of rho f, this is the prime, times A. And you will see when we replace this, now we have A here. So it's going to be very simple. We have the boundary factor. Well, this factor usually, if this is minus infinity and infinity, rho is going to 0 because rho must be normalized. It has to decay. If A and B are finite, so if we have a confined in a box, for instance, a stochastic differential equation where X evolves into between some boundaries, then this could, in some occasions, this could be different from 0, but not usually. This is always 0 in the boundaries. There is a problem with the boundary. The boundaries are the points where G is equal to 0, and in these points there are some problems, but well, in most applications, this is equal to 0. It's equal to 0. So you can neglect it here. And we have now this term is going to be equal to that. Now let's go to the second term. The second term, we do the same. In the second term, now I will forget about we will assume again that the boundary is 0. This factor is 0 in the boundary. So now we have an integration by parts. So I have only the second term minus the derivative of, in this case, the derivative goes to rho g squared. and we have this result. Okay, this is the first integration by part, but now we want to get rid again of the first derivative, so we will make a second integration by part, and then if I make a second integration by part again, not neglecting that this term is 0, so I get minus again, so it's a plus, and then this derivative goes to this one, so I can remove this derivative and put it here. So this is this term. So now we can put everything together and get, and let me put everything in the left hand side. So I take this as a minus, and everything multiplies by a. You see that there is a here, so I can extract the common factor a, and then I have a plus, because when this goes here, this goes as minus, but there is a minus here, so it's a plus, and here is a minus. And this must be equal to 0. So we have put everything to 0. Since this is for any a, and this is the nice trick, this must be equal to 0. Because this is for any a, this is equal to 0. And now we have it already. This is an equation. Now we go back this to the right hand side. So let me write this equation. Partial of x of t equal minus, I will write it complete, the complete equation with all the dependencies, so you can see. Oh, yeah. So there is a g square. Sorry, here is a g square. So I don't think I can write it. Okay, so this is the Fokker-Planck equation, the famous Fokker-Planck equation. This is an evolution equation for rho. It's a partial differential equation. There is no any problem of interpretation here. Well, we have already interpreted the equation as Ito, but this is the interpretation. This equation can even be solved for a small. I mean, for 1D, in one dimension. In the one dimension, it can be, at least in the stationary regime. Okay, this is, if you have this equation, this is the evolution of the probability density. What is the result for Stratonovich? Okay, for Stratonovich, so if we start with the Stratonovich equation, you see I don't use the little circle. Now I use the circle, the little circle. Okay, so what is, how can we derive the Stratonovich? If we want to repeat the derivation, the crucial point, which is that the average of A times the noise was 0, we cannot do it now. So we could try to make the same derivation using the Novikov theorem, and there are a lot of papers with this derivation. But we have a much simpler option, which is, okay, we know the equivalent of this equation, the equivalent in Ito. So we can go to our last result that tells us that this equation is equivalent to this one. Now we have this term, but interpreted as Ito. So this is the interpretation of Ito, and now we know the Fokker-Planck equation for the Ito case. So we know this one. No, so we can just apply this thing. So we have minus f. Now I have this term here as well. You see, this comes from here. So I have a minus with a, so here instead of f, I have to put all the deterministic part. So I will have minus f and minus gg prime. So I have this one plus this. And this would be the Fokker-Planck equation for Stratonovich interpretation. Usually this is simpler to write because you see here I have gg prime. So if I have the derivative of this product, sorry, this is g squared. It's a bit, it's a small here, but okay, this is a g squared. So one can take these two terms. You see that this term is, I can get the derivative of a product, and I can get the product, decompose this in a product of g times g rho. So this will be one of the terms. So you can write this as this one. I think I have a mistake here. Yeah, I have a mistake. When we derive the equivalent of this with Ito, it was on the other way around. So this is a plus. Sorry, now I realize my error. There is a plus here. There is a minus here. And now it's fine. And now this derivative, if you expand this derivative, you get g rho g prime, which cancels with this, and then g, the derivative of g rho. Okay, now it's fine. And this plus is because, let me go back to the, what we found is that if, this is the result that we found in the previous slide. If this is Ito, this is Stratonovich. Here there is a plus, but now if you want to do the other way around, if you interpret this as a Stratonovich and you want to find the equivalent Ito, this should be a plus because it is a okay. So this is what happened in here. So we have a plus, and now it's yeah, and now the equivalent, the Ito equivalent to this Stratonovich is with a plus. So it comes with a minus here, and here I have the derivative. Look at the first derivative with respect to x. The derivative of g squared rho, if I decompose g squared rho as g times g rho, then I get g prime g rho, which is this one, which cancels, and then g rho prime, which is this one. And this is usually a better way to write the equation. We can now write it like that. It's a nicer way of writing it. This is the Fokker-Planck equation for Stratonovich. And this is a nicer way because this part can be, this can be interpreted as a operator, the operator derivative times g. And you see there is derivative times g, so it's derivative times g squared applied to rho. And this has some interesting, and here you see that you have the same operator derivative with respect to x times f. So this is what it is called a Lie derivative, and it has a nice properties. Okay, so this is Fokker-Planck equation for Ito and for Stratonovich. They're of course different. if G is non-constant. If G is constant, you see that, well, G is essentially, you can absorb the constant in sigma squared, so G is 1, and you get just the same equation for Stratonovich and Complutense. Okay? Any question? No. So the two equations, the Ito and the Stratonovich, can be written as what in physics we know as continuity equations. And okay, this is the way we write the Ito. This is the Ito, no, because it's the Stratonovich is there should be a parenthesis here, this operator square. This is the Ito, and you see that there is a derivative in x, so we can put this as the derivative of a function, and this function is the current. This is called a continuity equation. This form of equation, the derivative of something with respect to time equal minus the derivative with respect to x is a continuity equation. Probably you have heard of that. No, it's an equation where if I integrate rho in an interval, I get that the change of the total mass. This is the rho is like a density. So the total mass in an interval is this function j in the ends of the interval. And this is generalized to several dimensions, replacing derivative. This should be a divergence. So the derivative of a density is always minus the divergence of a current, and this has this is a probability current. So how much probability crosses a given point x at time t. So the two equations can be written as continuity equations with a different form for the current. The Ito current, well, you can see it from here. The Ito current is going to be plus F rho let me rewrite the equation here, because this has a this term of the current has a very nice interpretation. This is really a current of probability. And why is F rho? You could see this rho as also the number of particles at position x and time t. If you see this as x as the position of a particle, and you have an ensemble of particles, this will be the current of particles crossing x. And the current of particles is precisely the number of particles, which is rho, times f, which is the velocity. So this term tells you what is the current due to f, this is called the drift. But it has another term, which is this one. And the Stratonovich is very similar, but the G is out of the derivative. And these two terms, these are called diffusion terms, because the current, you see, well, this is easy to G if G is constant. If G is constant, the current is proportional to this term in the current is proportional to minus the derivative. So if rho is an increasing function, the derivative is positive, and sorry, here it's negative. The derivative is negative, so the current is positive because of this minus sign. So the current points to the right, and here the current points to the left. So this term is responsible of currents that are diffusive currents. So they try to make the probability density as more flat as possible.